I welcome all the participants for this GAN course. Now we will be delivering the tutorial 2 that will be on the topic calculation of diameter of injector nozzle, ignition delay, and its impact on IC engine. So I welcome Professor Wangmin sir to deliver this particular tutorial. Over to you, sir.
Okay, yes, thank you. So we are continue to introduce the tutorial. This is the first one for me. Okay, so firstly, I want to introduce the major components of the injection system for these engines. So the most important one, of course, the fuel injector, correct? Just I will show you how the fuel injector works, correct? And the second one is a high pressure fuel pump. Okay, this one can increase the pressure from a fuel bomb, okay, 3 bar, 2 bar, or 4 bars into a few hundred, even a few thousand bars, right? And the third one is a plunger feed pump. Okay, this is a pump, actually it's a low pressure pump. This one used to draw the fuel from the fuel tank and at the same time increase the pressure by a few times. Okay, by increase the pressure a few times. And between the fuel tank and the plunger feed pump also had coarse filter. Okay, this one can help to clean the fuel. Can help clean the fuel, remove the big particles, all the impurity contained in the fuel. Also have a fine filters. Okay, this one can help can further remove the smaller particles contained in the fuel. Okay, and the pressure relief valve can return the uninjected fuel, okay, from the fuel injectors to the fuel tank to avoid the overpressure. Okay, so in the compression ignition engines, the combustion process is initiated by the spray, correct? By the high pressure fuel injection spray. So here we show you the spray structures. Basically, the fuel structures consist of two parts. The first one is the core of the jet. This core of jet is a liquid. It's a liquid. And it is surrounded by this called fuel admixture. Okay, actually this is a surrounding region. Actually, it's a fuel admixture. Okay, fuel admixture. So consists of two parts. The surrounding one, okay, this one actually is combustible, and the core of the jet is liquid, cannot be burnt. Okay, cannot be burnt at this moment. Correct. So this one is a fuel injection nozzle. Fuel injection nozzle. So there's a pressure difference between the inside and outside. Okay, inside we call the injection pressure, and the outside pressure is the in-cylinder pressure. Okay, it's a back pressure or in-cylinder pressure. Correct. So here we'll show you the two different conditions of fuel spray. So first one says no air swirl, no air swirl. And in the second design, we have air swirl. So we have a circular air movement. Okay, so by this circular air movement can help to break the spray, so that we can improve the fuel and mixing process. Correct? Okay, can improve the fuel and mixing process, thereby can improve the combustion process. Okay, so that's why actually in the video just I show you, correct, a strong swirl is formed in the engine, correct, in the combustion chamber. You can design the intake valve so that the intake air enters the cylinder along a certain direction, correct, along the tangential direction, thereby form a swirl. This swirl is important for these engines because this swirl can help to improve the fuel emission process and enhance the combustion process. Okay. So we can see here, this is a multi-hole injectors. Okay, we have 6 injection hole, correct? So we can say actually its wall is formed, correct? So we can see the flame actually is not radial, correct? Instead, we can see the flame is rotate. Okay, it's rotate, which means a swarm is formed inside, correct? So help to improve the fuel emission process and increase speed up combustion process. Okay, so for these engines, the combustion process basically can be divided into 4 stages. Okay, so first one is ignition delay. Okay, as a position, for example, the fuel injection start at about 19, okay, about 90 degrees CA before TDC. However, the combustion process only start as a position. It is about 10 minus 10 degrees CA minus 10 degrees CA. So from here to here, actually this is an ignition delay, correct? So this time is ignition delay time. Okay, so it's the time from the start of injection until the combustion process starts. So this duration is the ignition delay time. Okay. For different engines, for different fuel, case the ignition delay time is different. Different. Later, we introduce the major factors of affecting the ignition delay. Okay, and the second one is a rapid combustion process. Okay, rapid combustion process. So from the start of combustion process until the peak pressure. So this is a period. It's called the rapid combustion process. Okay, this process actually, because in the ignition delay time, a lot of fuel will evaporate to form with the air, form a combustible mixture, correct? So once combustion process stops, then the combustion process will be very fast. Okay, that's why in the second stage, we can see the pressure increase very fast because this one is a premix combustion process. Okay, the premix fuel will be burnt in this period, and this process is very fast. That's why the pressure increase is very fast in the second stage. Okay, then in the third stage is a control combustion process. Actually, from this video, we can see this fuel injection is a duration, correct? It's a duration. You can see when the fuel is injected at certain time, the combustion process also is taking place. Okay, it's taking place inside, correct? So this process is a controlled combustion process. It is controlled by the fuel injection speed and also controlled by the fuel emission process. Okay, so this stage is a controlled combustion process. So the third stage is controlled combustion process, and the last one is after combustion process. Okay, which means okay, when the fuel has been injected, all the fuel has been injected, but the combustion process is not stopped immediately, correct? Okay, so the remaining fuel will continue to burn until all the fuel are burnt. Okay, so the last process is after burning period. After burning period, correct? Okay, so let me show you a video control of ignition timing. Okay, so in this video, actually, we show you the combustion process in the gasoline engines. Okay, it's not diesel engines in the gasoline engines, but the combustion process, the ignition delay time, the ignition stage more or less similar. Okay, so we use this video to explain. Okay, what kind of factors affecting the combustion process affects the ignition timing. Okay. Okay, so you can see at point 1, a spark will be released for gasoline engines. And at point 2, the combustion process starts. Okay, so this period is called ignition delay time. Okay, ignition delay time. Then from point 2 to point 3, okay, so this process is a forced combustion process. So there, because again, during the ignition delay time, a lot of fuel will evaporate and form a mixture, a combustible mixture. So once combustion process starts, then this combustion process will be very fast. That's why the pressure increase very fast. Okay. Okay, then from point 3 to point 4 is after burning. Okay, after burning. So this gas engines combustion process is divided into 3 stages. For these engines, combustion process is divided into 4 stages. But actually the whole combustion process more or less similar. Okay. Okay, the next one I want to introduce is how to what kind of factors will affect the ignition delay time. How can we adjust the ignition time to produce the optimal performance? Okay, so this one assumes the engine speed is 1000 RPM, and this one increased to 2000 RPM. Then we can see because the ignition delay time in terms of milliseconds, in terms of absolute time is the same. Okay, so because this case the engine speed is increased by double, correct? Which means the crank angle from here to here, from the start of a spark release until combustion process starts. So this ignition delay time in terms of milliseconds is the same as this one. However, if you change into crank angle, then what happened to the second case? Maybe you guys can tell me what's the crank angle change, okay, from the start of a spark release until the combustion process for the second case. First one, 1000 RPM, second one, 2000 RPM. First one, assuming the crank angle in the ignition delay time in terms of crank angle is 10 CA. Then how about the second one? What is the crank angle for the second case in terms of ignition delay? Anyone knows? Okay, also again, of the first case assumes the engine speed is 1000 RPM, and the second case is 2000 RPM, correct? And also assume the ignition delay time in terms of milliseconds is the same for 2 cases. Okay, so the first case, if we change the the ignition delay time from milliseconds to crack angle, it is 10 degrees CA. So how about the second case? In terms of crack angle, what is the ignition delay time for the second case? Anyone knows?
Sir, the crank angle increases. Like it will,
So what is
it will
the
incline by 4.
what is the ignition delay in terms of crack angle for the second case?
The ignition should happen more no sir, in small time the ignition should happen again and again. There will be more fuel unburnt in the
Okay. Yeah, actually in this case, okay, because at 1000 RPM, the ignition delay time is 10 CA, correct? Then when the engine speed increases to 2000 RPM, which means as soon as the absolute time is the same, okay, then in terms of crack angle, will be changing to 20 CA, 20 degrees CA, correct? Understand? 20 degrees CA. Correct? So we can see at higher engine speed conditions, okay, for this case, second case, if you maintain the spark timing at certain time, then we can see the peak pressure will drop. The combustion process will be retarded, correct? The peak pressure drop and the combustion process also will start late. Okay, we also will start late, correct? So as a result, the efficiency will drop. So for this case, when the engine speed increases, we should advance the ignition timing. So the ignition timing should start from this position instead of 0.1. Okay, so we should start from this position. We should advance ignition timing, correct? Okay, so this is the effect of engine speed. Higher engine speed condition, usually you should advance ignition timing. Okay. Okay, the second one is the engine note is impact on the ignition timing. Okay, this one is lower engine note conditions. Okay, this one is a higher engine note conditions. So can you see the difference between these two? This one, this is okay. This is a ball means the few droplets. Okay, this one means a few droplets. So what is the difference? So you can see at higher engine conditions, more fuel is supplied or injected into the engine, correct? At lower engine conditions, less fuel is supplied to the engine, correct? Okay, so at higher engine conditions, we can see the combustion process is much faster than this one. So here we can see at higher engine conditions, because more fuel are supplied to the engines, and the combustion process is faster than this one. Okay, so for when the engine is operating at higher engine conditions, we should retard the ignition timing. Okay, we should retard the ignition timing. Otherwise, the fuel will be burned too earlier. Correct? And we reduce the efficiency, because if too much fuel is burned in the compression stroke, then the efficiency will drop. Correct? So at different engine conditions, the ignition timing also should be changed. Okay, the ignition timing should be changed. Higher engine conditions, the ignition timing should be advanced, retarded. At lower engine speed conditions, the ignition timing should be advanced. Okay. Okay, so here we show you the major factors affecting the ignition delay time. So first one, the completion ratio. Basically, the higher the completion ratio means the higher temperature, correct? Okay, higher completion ratio means higher temperature, correct? So we can see with increase of completion ratio, the temperature will increase. So the ignition delay time will decrease, correct? Higher temperature means faster combustion process and the ignition delay time will decrease, correct? So at higher completion ratio, you should retard the ignition timing because the ignition delay time will decrease, okay? At the same time, higher completion ratio also means lower auto ignition temperature. With increase of the completion ratio, also the auto ignition temperature will drop. Why? Okay, so first one is easy to understand. Higher completion ratio means higher maximum temperature and shorter ignition delay time, correct? So how to understand the second one? By increasing the completion ratio, the auto ignition temperature will drop. Why? Actually, I can go back to here. Because at higher completion ratio means the density, the fuel density, fuel and mixture density will be increased. Okay, so the distance between the droplet the molecules, the fuel droplet molecules and the viscous air molecules will decrease. Okay, the distance will decrease. As a result, okay, there more chance for the fuel molecules to contact with the air molecules. Okay, thereby can improve the combustion process, increase combustion process. Okay, that's why the auto ignition temperature will drop as we increase completion ratio. Okay, the second one is the engine speed. With increase in the engine speed, okay, the loss of heat during compression will decrease, result in the rise of both the temperature and the pressure for the compressed air. Thereby can reduce the delay periods, ignition delay time, correct? However, in terms of a crack angle, the ignition delay time will increase. Okay, just as we had discussed already, correct? The ignition delay time in terms of a crack angle will increase at higher engine speed. Okay, so as we increase the engine speed, the ignition delay time, the ignition timing should be advanced. Okay, should be advanced. Okay, so next one is output. Okay, so output actually means the engine load, correct? The higher the engine load, the higher engine power output, correct? So with the increase in the engine output, the fuel air fuel ratio decrease means the fuel air ratio increase. Okay, so the operating temperature will increase and ignition delay time also decrease, correct? This one from the video we had explained already, correct? The next one is the atomization. Higher fuel injection pressure can increase the degree of atomization. Okay, at earliest lectures in the previous lectures we have introduced. Okay, higher fuel injection pressure, the fuel droplets will become smaller. Correct. So the fuel evaporation and the fuel mixing process will be improved. Okay, as a result, the ignition delay time will decrease. The ignition delay time will decrease. At better atomization, higher fuel injection pressure conditions, correct? Okay, the next one is the fuel injection timing. Okay, this one we had discussed in the class, in the first class today, correct? We had show you compare the two different ignition timing, injection timing, correct? So we can see the injection timing has a big impact on the performance of the engine. Okay, now we're going to discuss at different fuel injection timing, what is the ignition delay time? So this one, assuming the fuel injection time is minus 27 degrees CA before TDC. The second case is minus 18. Third case minus 9. So comprises 3 fuel injection timing. The ignition delay time will decrease. Okay, will decrease. Why? Okay, with the increase of the from 27 to 18 to 9, the ignition delay time will decrease. Why? Can you guess? Maybe, yeah, think or guess. Why at 27 degree CA, yeah, the ignition delay time is longer than that at 9 degrees CA, when the fuel injection timing. While the ignition delay time at this position is longer than the ignition delay time at this position. Anyone knows? Okay, yeah, actually at this time, we can see the pressure is lower than this position, correct? Okay, at this position, the pressure in the cylinder is lower than that, okay, than this position, correct? Which means that this position, okay, firstly, the pressure is lower, and secondly, the temperature also is lower, correct? So the lower temperature, lower pressure means the ignition delay time will be longer, correct? At the position, the pressure is higher, the temperature also is higher, so ignition delay time will decrease, correct? Okay, the next one is a quality of fuel. Yes, different fuel has a different self-ignition temperature, correct? For example, diesel fuel, the auto ignition temperature is about 215 degrees CA, and the gasoline fuel is about 290 degrees CA, and the hydrogen is about 300. Okay, it's more than 400 degrees CA. Degree, yeah. So for different fuels, the self-ignition delay time temperature is different, correct? So the lower the ignition delay temperature, okay, then the lower the ignition delay time, correct? Okay, so its lower self-ignition temperature results in a lower ignition delay period. Okay, again, fuels with higher C10 number, usually the ignition delay time also decrease. Okay, will decrease. Other properties affecting the fuel ignition delay time includes continuity, latent heat, viscosity, and surface tension. Okay, this one is easy to understand. Okay, the fuel is if the fuel is easy evaporates, then okay, the fuel emission process will be better. So the ignition delay time will be reduced. The next one is latent heat. Okay, the latent heat is the heat energy required. Okay, for the liquid fuel become gas fuel, correct? So the greater the latent heat means the more heat energy will be absorbed for the evaporation process, correct? Then the temperature will drop. As a result, the ignition delay time will be increased, correct? Okay, so the next one is the viscosity and the surface tension. Okay, this one, a higher viscosity or higher surface tension will affect the fuel evaporation, correct? Thereby, the ignition delay time will be increased. Okay, ignition delay time will be increased. Okay, so next one is the intake temperature. This one is easy to understand. Basically, by increasing the intake air temperature, yes, we can reduce the ignition delay time, correct? Because higher temperature, correct, can reduce the ignition delay time. However, by preheating the intake air, what happened to the density of the fuel or to the air? by increasing the temperature, which means that the density will drop, correct? So less pressure charge will be supplied to the engine, which means the engine will produce less power, correct? And the power density will drop. Okay, so usually we don't preheat the intake air because by this way, the engine of power, the efficiency will drop. Okay. Okay, so last one is the intake pressure. This one is easy to understand. We use a turbocharger with a supercharger to increase the intake pressure. So we can reduce the ignition delay time because of the density increase, correct? And the auto ignition temperature will drop, correct? And the flame, the combustion process will be faster, correct? So the ignition delay time will be reduced at higher intake pressure, okay? Okay, so next one I want to introduce a few quantity and the size of nozzle orifice, how to design the fuel injection hole, the hole size, okay? How to calculate or design the fuel injection nozzle hole, okay? So basically, the fuel injection velocity can be calculated by using the equation, this equation, BF. This one is the fuel injection velocity equals to CD times square root over 2 times the pressure difference. This pressure difference, P injection, is a fuel injection pressure in the injector, okay? And the P cylinder is the pressure in the cylinder. Okay, so this P injection minus P cylinder is the pressure difference between the inlet and outlet of the injection hole, correct? So the greater the pressure injection, the pressure difference, the higher the velocity. Correct? This one is easy to understand. Correct? Next one is divided by rho F. Rho F is the density of the fuel. Okay, so by using this equation, we can find out the fuel injection velocity. Okay, fuel injection velocity. CD is the coefficient of discharge. Okay, it's a flow coefficient. Flow coefficient, because we know on the inner surface of the injection hole, it is not smooth. Okay, it is not smooth. It is rough. Okay, so the actual flow speed, flow velocity will be lower than ideal conditions. Okay, because we'll have friction losses. And as a result, the actual flow rate will be lesser than the ideal conditions. That's why we have to times CD. Okay, CD is a flow coefficient. Okay, the next one I want to introduce is the volume of fuel injected per second, Q. Okay, this Q is in terms of cubic meters. Okay, in terms of cubic meters, volumetric flow rate, volumetric flow. Okay, so the volume of fuel injected per second, Q, can be given by the following equation. Okay, first one, the fuel injection area. Okay, this one is the flow area. 1/4 pi d square. Okay, d is the diameter of the fuel injection hole. Okay, so 1/4 pi d square is the flow area for single injection hole, correct? Then times the n is the total total area for the fuel injection, correct? For multiple fuel injection holes, then the total fuel injection area is 1/4 pi d square times n. N is the number of fuel injection holes. Okay, so this one is the flow area. You can use the A replace this one, correct? And times VF. VF is the fuel injection velocity. So A times BF is a volumetric flow rate. Okay, A times VF is the volumetric flow rate. Okay, then times the time for one injection. Times time for one injection. Okay, this is a time for one injection. Okay, theta is the duration of injection in terms of crank angle degrees. Okay, because we know, let me draw a graph. Okay, fuel injection duration basically is about about 20 degrees CA, for example. Okay, this is just an example. Okay, assuming the fuel injection duration is 20 degrees CA, right? So this is fuel injection duration in terms of fraction for the whole circle. Then it is 20 degrees CA divided by 360 degrees CA, correct? Here's the fraction. Okay, we change this triangle to fraction. Okay, then it's 20 divided by 360, correct? Then assume the time, okay, for single, for one revolution, or for one not cycle, sorry, for one revolution is 16 divided by ny. Okay, n is the engine speed in terms of RPM. In terms of RPM, okay, n is RPM. Okay, R is revolutions. PM is per minute. Okay, so RPM is revolutions per minute, correct? Okay, so assume n divided by 16 become revolutions per second, correct? Right? Revolution per second. So 1 divided by n over 16 become what? The time for one revolution, correct? So 60 divided by n is the time for one revolution, correct? This one is the time for one revolution. Then this one times the fraction, then becomes the time for one injection. Okay, so that's why we have this one. Theta divided by 316 is changed to a fraction. That times the time for one revolution. So we can find out the fuel injection timing. Okay, fuel injection time for one reinjection. Okay, now understand? Okay, so this one is delta T, the fuel injection time for one injection. Okay, then times the number of injections per second. Times the number of injections per second. So we can find out get the total time in 1 second. The total injection time in 1 second. Okay, so y like this. Ni is the number of injections per second. Okay, divided by 16. So Ni, okay, Ni for 4 strangers equals to Ni equals to half n. Okay, for 4 strangers. For 2 inches, Ni equals to n. It's the same as the engine speed. Why? Why for 2 inches is n, for 4 inches is half n, the number of injections. Anyone else? Why this 2 is different? The number of injections is different for 4 inches and for 2 inches. Anyone else?
Number of times the fuel is injected in 4-stroke and 2-stroke are different.
Yes. Okay. So for 4 inches, okay, every 2 revolutions, there's only 1 injection, correct? But for 2 inches, every revolution, okay, there's 1 injection. That's why for 4 inches, okay, the fuel injection timing, not timing, okay, the number of fuel injections equals to the engine speed divided by 2, correct? And for 2 inches, okay, the number of injections equals to the same as the engine speed, correct? Understand?
Right, sir.
Okay. Okay, great. Yeah, so we are going to introduce examples and we can close this tutorial. Okay. Yeah, calculate the diameter of the fuel orifice of a fossil engines, which develops 25 kilowatts per cylinder at 2,500 RPM. The specific fuel consumption is 0.3 kg per kilowatt hour. The fuel is injected at a pressure of 150 bar over a correct angle travel of 25 degrees CA. The pressure in the combustion chamber is 40 bar, and the flow coefficient is 0.875. Specific gravity is 0.8762. Okay, so we can use the equation just how we can introduce here. Can use this equation to calculate. Okay, firstly, we find out the duration for injection, okay, per second. So we can use this equation, correct? Use this equation. So duration for injection is 25 degrees CA is the theta divided by 316 times this one. So we can find out the time for injection, correct? For one injection, okay? The duration of injection for one single injection, okay? Actually, it's directly use this equation, theta divided by 316 times 60 over n. So this one is the duration of injection in terms of seconds. Okay, so next one is the velocity of injection. We can directly use this equation to find out. So CD is given 0.875, correct? The injection pressure is 150 bar, and the in-cylinder pressure is 40 bar, correct? Again, we should be careful here. We should change into standard unit. Standard unit is Pascal, correct? It's not bar. Okay, so that's why we times 10 positive 5, because we changed the unit from bar to Pascal. Okay, so can find out the fuel injection velocity is 138.65. If you don't change this one, okay, then this value will be very small, okay? Will be only 1.17 meter per second. Okay, will be very small. Okay, the next one is to find out the volume of fuel injected per cycle. Okay, the volume of fuel injected per cycle. So this one actually is use BSFC. Because BSFC is given, it is 0.3 kg per kilowatt hour, which means the fuel consumption is 0.3 kg when the engine produces 1 kilowatt power for 1 hour. Okay, so BSFC times divided by 16. Okay, this one is 0.3 kg per hour fuel consumption, correct? So divided by 16 become the fuel consumption per minute, correct? So we have BSFC divided by 16 becomes the fuel consumption per minute. Then times up power. Then is the fuel consumption. Gets the fuel consumption for the cylinder, for the whole cylinder. Because BSFC is a fuel consumption for 1 kilowatt hour. Okay, but this engine is able to produce 25 kilowatts for 1 cylinder, correct? So for 1 cylinder, run for 1 hour, then should use a BSFC times 25. Okay, times 25. Okay, then times the number of cycles divided by the number of cycles or the number of fuel injections. Okay, then we can find out each time how much fuel is injected, correct? Okay, this one is the fuel consumption in 1 minute. Okay, then divided by the number of cycles or the number of fuel injections, correct? So can find out each fuel injection how much fuel is consumed. Okay, so this one is in terms of mass, then divided by density. We can change the mass to volume. We change the mass to volume. Okay, then we can find out gas of fuel injection amount is 0.114 times 10 positive negative 6 cubic meters per cycle. Correct? So this is a volume injected per cycle. And then we can find out the flow error. Okay, so flow error. Because the flow error equals to the volume injected, Okay, volume of fuel injected per cycle divided by injection velocity divided by injection time, correct? So can find us the flow error 0.43 times 10 power to minus 6 square meters. Okay, and again, the area of our orifice is 1/4 pi d square. So can find out D. The diameter is 0.792 millimeter. Okay. Okay, so yeah, that's the end of this tutorial. We still have 2 minutes. Okay, so that's a homework. You guys can you can try by yourself at home. Okay. Yeah, this can be part of the final examination. So you can try by yourself at home. Okay. So we still have 2 minutes. We can if you have any questions, we can discuss. Okay, any questions?